All right, we're going to go. Hi, everybody. Hope you're staying warm and safe and all the things on this snowy day. I'm going to switch to document camera here. Here we go. And we're going to make sure I got a pen here. Several pens. Just grab one I like. What are we doing today? We're going to review for exam one. Of course, this is for a calculus-based physics course. If you're joining us from somewhere else on the internet, that's what we're doing today. We're going to talk about motion and vectors is going to be our goal. In here is going to be a quiz for my students, and we'll talk more about that as we get further along. So I'm probably not going to work any examples in here. That's what I'm going to host a Zoom session with my students to go over those, any homework questions my students have. So no, this is really just going to be a skeleton outline of major topics that would normally show up on a first exam for Physics 1. All right, this is what's going to go on my exam. One of the big things is units and dimensions. Right? Units and dimensions. That's a big topic, and be able to use conversion factors. Now, for me, I'm not going to ask you to have any conversion factors memorized, except for like, I would say no days, seconds, your basic time conversion. Know these: Earth days, seconds, hours, and years. Right? Be able to go, if I gave you something in years, could you convert it to seconds and vice versa? And that's outside of that, any other units of length or any other units of mass or anything like that, that if I do ask you to convert those, I will give you the conversion factor, and I'm just asking you to apply them. I probably won't give you conversion factors for these, though. I'm going to expect you probably know these from normal life. But if you need them, you can ask me in class, and I can kind of I'll give you numbers. That's doable. Um, Also, major topic would be we spent some time and we've talked about basically there's two main topics or three main topics, I guess I could point to. One is this fundamental units and dimensions. The next is vectors. And the other one would be motion. Right? Being able to describe motion. So these are the three main topics, and heavy emphasis being on motion. I don't know how many problems are going to be on the exam. I've got a pretty good idea what it's going to look like. But there's going to be, if I had to guess, 10 or so problems. You guys get, an hour and 25 or an hour and 40 minutes to do it. It's basically, it's a 2 hour time block, so to speak. So you'll get 1 hour and 40 minutes. I'm going to give details that are specific to my class. You can skip ahead a little bit if you're joining us from somewhere else. So again, exam one for us is going to be in the next class period. For us, that is February 17th. Excuse me, February 17th for us. Again, 10 problems or less probably is my guess. Some of those problems will have multiple parts, though, right? So the biggest thing is look at how many points are allocated where, and kind of allocate your time accordingly. If you look at a problem and you're not really sure how to do it, and it's a 10-point problem and there's a 20-point problem after that, I wouldn't, if you look at the 20-point problem, like, well, I know how to do that. We'll maybe do that one first and come back to the 10-point problem if needed, but do all of them you know how to. What else we got here? It is closed book. And it's closed book. It's also closed neighbor. I think that should be obvious. It'll be in class. Right, so our class meets 3 to 4:40 p.m. So you'll have 1 hour. You'll have the entire time, 1 hour and 40 minutes. It'll be on paper. A few of you have asked, is it going to be on our homework platform? No, it's not on the computer. It is on paper. I, in general, am not really interested in your ability to find solutions on the internet. I'm interested in your ability to show me how to, show me what you learned doing the homework and going through class so far. So no, the exam will be on paper in class, and you will get. I don't mind you using one sheet of notes. I don't mind you using a sheet of notes. It'll be what we call a standard size A paper. That's up to 8.5 inches by 11 inches. So just standard. I mean, I've got engineering paper, which is that size. Copy paper, your standard paper you would put in a printer or copy machine would be fine. Sheet of notebook paper would be fine. It can be front and back. It can be front and back. I'm pretty liberal about your sheet of notes. It needs to be your handwriting. Okay. It needs to be your handwriting and not a photocopy. Okay. So I've tried to specify all the things, try to make it to where there shouldn't be any creative way to get an advantage out of this. Whatever you can physically write by hand on one sheet of notes, 8.5 by 11, is allowed. If you want to put 500 example problems on these, I would suggest you need to rethink your study habits, because that's it's probably not the best way to do this, but I don't mind that if you just want to copy down every single homework problem put on there and hope you get lucky that the problem I put on the test is like one of the homework problems. That's okay. I think there's a better use of your time and a better way to study, especially those of you going on in engineering, which I think is a lot of you. But honestly, any field of STEM, it's all about learning how to apply critical thinking. And if all you know how to do is copy a solution to from one solution to another, that's not going to serve you well in classes moving forward for just about all majors. So all that to say, I'm not super picky. I would encourage you to put fundamental equations on these, maybe an example problem or two. You can fill it full of example problems. I'm not going to tell you can't. I guess what I would say is, as you're doing the homework problems, notice which ones are what are the equations and concepts you're encountering, and what are the things you're having to look up as you're going through, and put those down on a sheet of notes. That would be helpful. But the goal here is the sheet of notes is, after you've kind of done the homework and you think about, all right, what would I need to survive this exam? What personally do I need? And that's what goes on your sheet of notes. And this ends up being as good of a study tool as anything. Even I remember even in classes where the instructor wouldn't let us have a cheat sheet, if you will, a sheet of notes. I would go ahead and make one up and just not use it on the exam, because I learned early that was just going through the process of figuring out what's so important to me that I want to put on this sheet of notes, so I've got it for the exam. Just going through that process is a really good way to set that information in your mind is very important, and your brain's a little more likely to hold on to it and be able to process it correctly. Last thing is a calculator. Right? As a calculator, and if you say, well, my phone's got a calculator on it, can I use my phone? No, I there's no internet on the exam, right? So as long as your calculator doesn't have internet, it's golden. Now, if you've got a fancy graphing calculator, and I know some of those do have some Wi-Fi capability. If I think I've got a problem, if I think you're just scrolling through information on your calculator looking for, accessing a solution or something like that, I'm going to swap it out for one of my calculators. I'll have a couple of backup calculators. One will be an old graphing calculator, and the other's just a standard scientific calculator. All you need here is just a scientific calculator, something that can do sine and cosine, multiplication, division, some addition. That's really all you have to have for this exam. So, if you have questions, concerns about your calculator, send me an email, bring it by. It's a lot easier to ask me for permission than it is to beg for forgiveness, because you normally won't like the latter. If you're not sure, ask me about your calculator. That's perfectly okay. All right. I think that's the logistics for the exam. I think that's the main things I need to cover on that. So from there, it's going to be, this is page 2 of something, 1 of something up here. Okay. So let's talk about, I mentioned earlier, there were kind of 3 main categories of topics. We're going to talk about, I've already probably talked all I need to talk about units and dimensions. And again, our test will mostly cover these 3 main topics, and this is probably the least of them, but it's still important. So that's probably about all I really need to say about units and dimensions. Again, it's not that it's not important, it's just that's going to be the introductory topic. After that, if we talk about vectors, if we talk about vectors, it's not a bad place to go from there. So if we expand on this idea of vectors just a bit, vectors are quantities that require a magnitude and direction. So vectors are quantities that require magnitude and direction. Know how to combine vectors through add and subtract. Know how to do a scalar multiplication. So scaling up a vector, or scaling down a vector by multiplying a scalar quantity to it. Different ways I can transform the vectors. And then also components, describing a vector as components, which the term there is often resolving a vector into its components. And that being its x and y components. Your text likes to call it polar form, which is magnitude and direction, basically. Right? And what we're saying there is, if I've got, again, just as a reminder, if I've got vector A And that vector A is at some angle theta measured from horizontal or measured from the positive x-axis. If I resolve this vector, that means I can add the x component of A to the y component of A. That means I can define vector A as the x component of A plus the y component of A, which we would often write this as the magnitude of that x component, the length of that x component, and its direction. Its direction would be in the positive x direction. We use the I vector to describe that, plus the magnitude in the y direction times, so this is its magnitude times its direction, the j vector. The j vector is a unit vector in the y direction. The I vector is a unit vector in the x direction. Okay. And then in polar form, this magnitude and direction, we could write this as vector A is equal to the magnitude of A at the angle theta. And if I write it this way, it is understood I'm measuring theta counterclockwise from the positive x-axis. Now, what that looks like is, of course, the magnitude of A, which in a lot of texts, they'll write it this way. They'll basically take, if you've studied matrices before, this looks like we're taking the determinant of vector A. That's kind of what we're doing. We would take the square root of the x direction length squared plus the y direction length squared. And all you're doing there is applying Pythagorean theorem. We're saying that a squared is equal to x squared plus y squared. And that gives us the length of that vector A. And then again, you can do your trig here and see that to find theta, I could take the inverse tangent of AY, the opposite side of theta, divided by AX, the adjacent side of theta. I could also do the arc sine of AY over A. I could do the arc cosine or the inverse sine of, or the inverse cosine of AX over A. And any trigonometric function to find this unknown angle is just fine. You have to knock the cobwebs off the trig just a little bit. But those are the main things to be aware of with vectors. And it's just simply being able to combine them a little bit, do some basic functions with them. And the reason that's important is because we're going to use vectors then to describe motion, motion of particles, motions of objects. A little bit later in the course, we'll use vectors when we're talking about the momentum, and we're trying to conserve momentum in a situation before and after a collision. So exam 3 we'll definitely come back to vectors, but we'll also use vectors in exam 2 material, where we're looking at Newton's laws and looking at how forces are going to cause changes in motion. And that, again, is our next topic. So we're going to use vectors to describe motion throughout the semester, but we need to be able to describe motion. And that's really kind of our goal on exam 1, unit 1 material in a physics 1 class, is understanding how we describe motion. Well, motion kind of comes down to 3 things. You're going to have position, you're going to have velocity, and you're going to have acceleration. I'm going to pause this here. So with this in mind, we just need to understand that there's a few ways we can describe both velocity and acceleration, which describes basically the change in motion. So you have what we call the average velocity. Right? If I measure the average velocity only in the x direction, I can measure it in the x or the y. But the average velocity is going to be the change, basically the change in position. So our text likes to use final minus initial. That's okay. So x final minus x initial divided by, you could say, t final minus t initial. A lot of times we just have t minus 0. So it just ends up being t in the bottom, but the change in position over a particular change in time. And then we talked about as this change in time gets smaller and smaller and approaches a differential size, then we start looking at what we call the instantaneous velocity. What is the velocity at any given instant in time? A very tiny differential change in time. Well, that becomes the derivative of x with respect to time. So if I have, I'm going to use a different pen. This seems to be getting worse. This pen's going to be a lot darker, but it should work. So if I have some function of x as a function of time, I just need to take the derivative of it to get the instantaneous velocity. And so this would give me a function of time, and then I can plug in, if I need to know, say, the instantaneous velocity at, say, 4 seconds, I could just plug in 4 seconds when I get this derivative. If I need the average velocity, I would need to know over what period of time, from 0 to 4 seconds, from 2 to 4 seconds, whatever it might be, and then find the position at those different times. Same thing with the acceleration. You can have an average acceleration, and again, I'm just going to define it in the x, but it's the same thing, whether it's the x or the y direction. And that would be the change in the velocity between, the final velocity in the x minus the initial velocity in the x divided by a period of time. So final time minus initial time. And same thing we saw with velocity. I can have an instantaneous acceleration. That's just ax if it's in the x direction. And that's going to be the derivative of the velocity in the x direction with respect to time. Let's be page 3 of something. What else we got here? Oh, and of course, as we've discussed before, this becomes the second derivative of x with respect to time. So if I take derivative of x, I get velocity. Take derivative of velocity, I get x, or I'm sorry, I get the acceleration. So the velocity will describe whether the value of x is increasing or decreasing. The acceleration will describe whether the value of velocity is increasing or decreasing, and it will describe the concavity, the shape of the x curve if I plot that x out as a function of time. So we've seen that in the homework a little bit. I know we did an example problem in class where we looked at the graph of position and compared it to velocity and acceleration, and we looked at how those change. So we've again, I'm not going to do any examples in here. It's really just kind of reminding us. My goal with a review session is basically the idea is I've shown you the theory in class once. You go out, you do some homework problems, you learn, you kind of try to apply that theory and try to wrestle with it. And then we come back on a review and we go back through and say, okay, remember all these theories, these, and hopefully after you've kind of seen it, then you've wrestled with it, and now we see it again, probably in a slightly different approach than how I did it the first time because I'm going a little faster. And the hope is this kind of helps solidify in your brain how these things work and how they're interrelated, which is really kind of what we know about how we learn is the more times we see it, the more times we process information, the more it begins to form synapses in the brain and begins to stick in the memory. So that's really what we're trying to do here is we're just trying to give you one additional exposure to the material and help your brain start really kind of forming it and solidifying it as you move forward. Now, as we describe motion, one of the first things we said is, hey, look, there's some really, calculus is cool and great and it works. Thanks Sir Isaac Newton and I think Lieberman and not Lieberman, I don't know, the other guy that helped and the people that made calculus. Thanks for that. And although when we're doing calculus on them, maybe we don't lump them, but it works. But there are situations where we wouldn't necessarily have to use calculus. And one of those is the idea of constant acceleration. So if my acceleration is constant, I have a set of very powerful equations I can use to find, to be able to describe the different motion. Those can take a number of different forms. I think this is pretty close to how your text presents them. You can say Vx final is equal to Vx initial plus AX times time. So if I have acceleration is just a constant quantity, then I can find the velocity in the x direction at any point given the initial velocity in the x direction plus the amount that velocity is going to change over time added to this initial velocity, and that will give me the final velocity. And we can do something similar with the x position. So the x final location, is going to equal the initial x location plus, there's a few ways I can do this. There's one way is I can say, well, I can add to it basically the average velocity, which would be a way I can find that is if the acceleration is constant, I can say, well, take the final velocity in the x direction plus the initial velocity in the x direction, divide that by 2, that gives me the average velocity over a period of time, multiply that average velocity by the amount of time, and that gives me the change in the x position based on that average velocity during that time frame. Because again, if it's constant acceleration, just a linear average of velocity will be fair enough for this. Had to sneeze there, so I paused the video. Okay. Another version or another type of equation we can use here is I can also find the final x based on the initial x plus the basically the change in x from the initial velocity over time, and then plus the effect of the acceleration. So 1/2 ax t squared. Now, if you notice, again, we said up here earlier, we said velocity being the derivative of x. And so if you take the derivative of this function, oh, sorry, you can't see that. If I take the derivative of this function down here, notice I get this function right here. Right? The derivative of x final is going to be the velocity x final. The derivative of x initial is going to be the velocity x initial. Or actually, I guess this guy is going to go 0. This is a constant. The derivative of this is that, and the derivative of this becomes that. Okay. The other thing I can do is another thing I can point out is notice if I take the derivative of this guy, the acceleration is just going to equal 0 plus this derivative, or the derivative of axt. Well, the derivative of axt is just ax. So ax, if acceleration is constant, then the derivative of this is ax plus is a constant, or plus the derivative of constant 0 plus ax. So ax is equal to ax if I take the derivative of this expression. Finally, there's this other expression that we derived that's very helpful if I don't know the time. So Vx final squared is equal to Vx initial squared plus 2 times the acceleration times basically the change in the x location, x final minus x initial. So again, we derived that one in class, and it's not a hard derivation, but it was kind of lengthy and tedious, so no reason to go back through that. But these are, I think your text presents a 5th one, which is basically, I think it's basically based on the average velocity if memory serves. But these are normally in most physics books, these are kind of the 4 classic constant acceleration equations that are normally put forward. And with these 4, you can do a lot, right? There's only 1, 2, 3, 4, 5, 6. There's basically 6 parameters. I've got 4 equations with 6 parameters. So if I know acceleration is constant, of the 6 parameters that you see here, I only need to know 2 of them, and I can use the other 4 equations to find up to 4 unknowns. So very powerful set of expressions. Now, there are a set of problems where you'll encounter that are what we call free fall. So if something is free falling, this is also, these equations apply, but they're in the y direction. We're talking about a constant acceleration in the y direction. If it's free falling, it's constant acceleration in the y direction, which is equal to minus g, minus the acceleration of gravity, being in the down direction, which would be 9.8 meters per second squared in the down direction. So again, let's just change all the x's to y's whenever I'm talking about motion in the y direction of its constant acceleration, and I just plug in the appropriate value of g. Now, what else we got? When a is not constant, you guys can just barely see that. So I gotta move some of my other sheets out of the way here. So when a is not constant, well, the expressions we had up here earlier where I take the derivative of v to get ax, and I take the derivative of x to get v. That's if it just depends on what am I given, right? If I'm given x as a function of time, I can take derivatives of it to get to velocity and acceleration. But if I'm giving acceleration, which is some function of time, then what I've got then is I've got, well, v as some function of time, which basically is just going to be vx final, if you will, right? Vx final, that's going to equal the initial x, or vx initial, I should say, vx initial. It's going to be the initial x plus the integral of the acceleration with respect to time. So if acceleration is some function of time, I just need to integrate acceleration. Again, I'm not going to worry about the constant here. This serves as my constant of integration, but if I integrate from 0 to t, then I don't have a constant here. This basically serves as the constant there. And to find position as a function of time, basically you're looking for what is the final location of x based on some initial location of x, right? X initial, plus then I'm going to integrate whatever my velocity in the x direction is with respect to time, because if the acceleration is a function of time, then the velocity is definitely going to be a function of time. So I'm going to integrate that with respect to time. And if you look at this expression right here, that's basically what we've done. Is you can also do it if acceleration is constant, right? If I take this expression, I integrate it, I plug this in to this integral right here. If I take the velocity and plug it in down to this integral right here, basically I get this expression here, that x final is equal to x initial plus the integral of this, which is vxit, plus the integral of this, axt, and that's axt. Integral of axt is 1/2 axt squared. So it does work if it's constant. It's just those are already derived for us. But if a is not constant, this is the approach we'll have to go. We'll have to find the net effect of the acceleration to describe the change in velocity, and we'll have to find the net effect of the velocity to describe the change in position. Okay. We've already talked about slope or change. V basically describes the slope or the change in position of x, or the area under the acceleration curve, and that the acceleration indicates the slope of velocity or the concavity of a. Okay, so that's motion in one direction. about motion in one direction. If we talk about motion in multiple directions, by the way, no three-dimensional stuff on the exam for me, for my class at least. And can't promise those of you who are joining us from somewhere else. I don't know if your instructor is going to put three-dimensional stuff on their exam or not. For us, is I will leave that to later courses as far as I'm concerned. We got enough other stuff going on. We've seen 3D stuff in the homework, and that I think is sufficient for our needs. If we talk about motion in multiple directions. And basically what we're going to do is we're going to combine what we've learned about vectors with what we've just learned about motion and put them together. And that's really all it boils down to. You have what we call a position vector. And a position vector is going to describe the location of our particle or of a particle or whatever it is we want to describe the location of. And so that means I've got this R vector is going to equal basically the change in the X location in the X direction plus the change in the Y location. And I know we said we're not going to do 3D on this exam, but it doesn't mean we can't at least mention that I could also add to it a change in the Z location. That's still true if I'm just dealing on the XY plane, motion in two directions. It's just this is 0 minus 0 in that case. So it's still technically there. We just, again, I'm not going to test you on that. You've seen it in the homework, and that's sufficient for me. Now, if we talk about the velocity vector, if I look at the actual velocity vector, the instantaneous velocity vector, well, that's going to be the derivative of basically the R vector with respect to time. So if I've got a function in time for these guys, I'm just going to take the derivative of each of those, right? The derivative of the X with respect to time in the I direction plus the derivative of Y with respect to time in the J direction plus derivative of Z with respect to time in the K direction. That's if I have to perform the calculus here. And so basically you just do each component at a time and then add them together into your velocity vector, right? If the problem is asking for the average velocity vector, just like we did with one dimension, it's really not much different. I'm going to find the position, the final position, minus the initial position, and divide that by the change in time, final time minus initial time. And that'll give me the average velocity, the average change in position over time. And the same thing with acceleration. Basically have the same exact thing with acceleration. So the acceleration vector is going to be the derivative of the velocity vector with respect to time. So it'd be the derivative of the velocity in the X direction times I plus derivative of the velocity in the Y direction with respect to time in the J. And if we have a Z, derivative of velocity in the Z direction with respect to time times the K vector. And you can also have an average velocity. That would be the final velocity minus the initial velocity over a period of time. Time final minus time initial. Okay. Now, a very common application we could have a particle where I'm given some position vector, right? Maybe this is some function of time, and I can take the derivative of that to find its velocity, and the next derivative to find its acceleration, or I could integrate backwards. That's all fair game. But the most common multidimensional, two-dimensional stuff that we'll work with, I'm not saying this is the only thing we'll work with, but it's the most common thing, is projectiles. Right? So projectiles, that is where your acceleration vector is equal to, there's no acceleration in the x direction, and it's a negative g in the j direction, or in the y direction. And so what happens then is you have a set of equations that you can write. Right? You've got x. Well, let's write. Let's start with. Let's draw a picture first. So you're going to get launched at some initial velocity, at some initial, and your text. I apologize. I get so used to using a subscript of a 0 to describe the initial. Let's make that bigger. I get so used to using not or a 0 to describe the initial. I forget that your text likes to use an I here, and that's okay. If this is the first time where you've encountered, hey, Steve, don't they just use the same thing from one text to the other? No, they don't. Welcome to the rest of your life as a scientist or an engineer. Learning what source you're working from, what nomenclature they use is, again, I apologize if I am the bearer of bad news. No, they very rarely do. They use exactly the same. There's some consistency, but anyway, your text likes to use the I for initial, where a lot of texts will use a 0 for initial, and that's fine. So we're launching some projectile at some initial launch angle, and it goes through a trajectory, right? And so that initial velocity is going to have an initial x component and an initial y component. And you find those just based off the trig of the triangle that I would draw, this being Vxi and this being Vyi. Right? So just doing some trig there, you find that initial velocity just ends up being Vi cosine theta I in the I direction plus Vi sine theta I in the j direction. And so those are your components, your initial components of the velocity. And then we find that your x location interesting. So what we can do is we can say, well, your x location, your x final location is going to equal your x initial location plus this Vi cosine theta I, which is just, this is just Vxi, is what that is. This is Vxi times time. And then your y location, y final, is going to equal y initial plus the velocity in the y direction. That's going to be Vi, the initial velocity in the y direction is going to be Vi sine theta I times t. And then you also, because it's accelerating in the y direction, you have to account for that acceleration. So it's going to be minus 1/2 whatever gravity is times time squared. Now, your velocity vector, we said earlier, is going to be the derivative of x with respect to time in the I direction, plus the derivative of y with respect to time in the j direction. So I can do that here. I mean, we know these equations are true. We've already seen these. These are just based off of constant acceleration equations where the acceleration in the x direction is 0 and the acceleration in the y direction is gravity. Now, if I take derivatives of these two functions, okay, what you find then is the velocity vector. If I take the derivative of this x expression here, well, the derivative of x is going to be, or the initial x is a constant, it's going to be 0. So it's 0 plus the derivative of this. Well, I've got this times t. So the velocity in the x direction then ends up being vi cosine theta I. And that's in the I direction. That is the derivative of this function here. Plus, for y, or for the y direction velocity, I'm going to take the derivative of this y function. So this is constant. That derivative of that is 0. Derivative of this is just going to be vi sine theta, right? Sine theta I should say. So that's the derivative of this term with respect to time. And then I'm going to take the derivative of this term. So I've got 1/2 gt squared. It's got a negative sign, so minus. This 2 is going to come down when I take the derivative. So it's going to be 2 times 1/2. That's just going to go to 1. The g is going to stay there. It's a constant. So it's going to be 2 times 1/2 gt, basically, or gt. That's in the j direction. So again, the calculus works. Just wanted to show you that. And the calculus works just fine. What that means then is that your velocity in the x direction, your final velocity in the x direction, if you will, is equal to this initial velocity times the cosine theta I, which is just the x direction initial velocity. And then your velocity in the y direction, your final y direction velocity, is going to equal this initial velocity times the sine theta I. This is the initial y direction velocity, minus, you have to subtract the change that gravity, the acceleration, is causing. So minus gt. I've just taken this. And so, well, this is the y direction velocity at any given time. This is the x direction velocity at any given time. It does not change, assuming we neglect air resistance. And as we've discussed, that's for engineers, it's a junior level class to look at fluid mechanics, where we talk about drag forces. I don't know about other majors, but at any rate. There is one last thing we've got to do, is talk about circular motion. But before we do that, I'm going to show you guys a quiz. So here's a quiz. Okay, so it's, unfortunately, I can't get it on one page. This is number 1, is a projectile. This is number 1, 5 points. This will be quiz 4. Going to be an online submission. 5 points. I don't know why the camera's not showing that very well. 5 points for number 1. You've got a projectile getting rolled off of a wall 2 meters high at a horizontal 2 meters per second. We want to know how far does it go out in the x direction before it hits this level ground 2 meters up. How far out does it go out here before it hits the ground? That's one problem. The second problem, and by the way, pause it if you need to get more information here. And then the second problem, we've got a particle's position as described by this position function. Right, I got a position vector there. I want you to find what is the instantaneous velocity and what is the average velocity between 2 and 4 seconds for this particle. So that's number 2. That's 5 points. So this will be quiz number 4. Pause it here, back it up, get that. I want you to take a picture of your work and send it to me on Canvas. I'm going to have an online submission. I'm going to make that available to you. So this is mostly checking to see who's watching the video. But yeah, I'll publish quiz 4 for you guys. And maybe it's, I don't know if it's quiz 4. It might be quiz 5. Whatever quiz it is, I'll publish it. And yeah, so the last thing to talk about is circular motion. Right, so we can, that's where we finished up. I didn't want to go too in depth, but it is in chapter 4. It's covered in the homework. And the main things we want to know about this is if I've got a particle moving in a circle, we have what our text calls centripetal acceleration, not centrifugal. Centrifugal is another thing that kind of doesn't really exist. But centripetal acceleration for an object moving in a circular path or a curved path is going to be the speed squared, the magnitude of the velocity, divided by the radius of curvature for the path it's traveling. For a circle, that's just the radius of the circle. And then if there is what we call tangential acceleration, that would just simply be the derivative of the speed with respect to time, which is equal to 0 for what we call uniform circular motion. So if something's moving in a circle, in a uniform circle, and so if I have a particle here and its velocity looks like this, its velocity is tangential, you will have what we call the centripetal acceleration towards the center of the circle, where this circle has some radius r. So your centripetal acceleration is found by this. The magnitude of this centripetal acceleration is v squared over r. Its direction is always pointed towards the center of the circle. It doesn't matter where we're at. If I'm over here, your speed or your velocity is always tangent to the curve being traveled. That is your centripetal acceleration pointed towards the middle. If I have tangential acceleration, it's going to be parallel to that speed. But if I've got uniform circular motion, there is no tangential acceleration. We saw that. I had some nice GIF images in class to try to demonstrate that a little bit. I'm only going to test you on uniform circular motion, by the way. Right? So that's, at least on this exam, that's all it's going to show up is uniform circular motion. So you may need to work with the centripetal acceleration somehow. There's some homework problems and kind of, I'm not going to do anything more complicated than what you see in the homework problems, maybe even less complicated. So that is a thing that we need to be familiar with. We will see circular motion throughout the rest of the course. And again, on this test, it's only going to be uniform. This exists, but it's going to be 0. This is what we're looking at for this exam. Okay. All right. I've got to get this video processed and then uploaded, and then YouTube will need to process it so you guys have access to it. And I want to try to have all that done by 3 o'clock. So I'm going to stop here, but I will be available in Zoom for my class for anybody that's got questions and wants to just stop in and say, hey, that's all fine. All right, guys, stay warm, stay safe out there.